Many real-world problems are affected by friction. Anytime two objects are in contact and experience a load that causes one to slide past the other or to want to slide past the other, friction should be considered. This video focuses on systems that can be modeled as rigid bodies that are experiencing friction. And to be exact, we're talking about dry friction, which is friction without lubrications. Systems that have lubrications are a subject of another course. With dry friction, the force is found using one of two friction coefficients. If the two surfaces are not actually sliding past each other, we use the coefficient of static friction, μs. If they are sliding past each other, we use the coefficient μk for kinetic friction. Keep in mind that static systems are systems that don't accelerate. They can be moving as long as they're moving at constant velocity. In most cases, μk is less than μs. In other words, it's harder to get something moving than to keep it moving. There's a model equation that's used to calculate friction force that looks like Fn times mu. And the thing that you need to keep in mind is that this is the max possible value. Friction is a reaction force, and as we change the load, the friction changes as well. And what this tells us is the maximum possible friction force before things start to change, either by sliding or accelerating. In the case where the system is not sliding to begin with, when the applied force is equal to the friction force Fn times μs, we have reached the maximum possible moment before this thing is going to slip and start moving. If we're in the sliding case and the friction force is equal to Fn times μk, we are at the maximum possible applied load before this thing starts to accelerate. So in either case, we could apply a smaller force, in which case F mu would just be the reaction force. The most it can ever be is given by this formula. And so a lot of times I like to think of it as less than or equal to. What I'd like you to do is continue to think about friction as a reaction force and realize that all we have to do to solve friction problems is add a new reaction force to our free body diagram. So for example, a rigid body that might be experiencing friction could be a ladder leaning against a wall. And that ladder has rubber feet that cause friction to take place at the point of contact on the ground here, so we'll write F mu. But we're going to assume that the friction force on the vertical wall is very small. The vertical wall here is going to supply a reaction force Fn, and I'm going to call that Fn2. There's a reaction force here at the bottom wall that I'll call Fn1 that stops this thing from falling through the floor, all of which is happening because acting through the center of gravity is the weight of this object. Weight always acts through the center of gravity. If you look for a moment here, you'll notice that we have three unknowns. We have Fn1, Fn2, and F mu. What that means is we need three equations. This is how these are different than particle friction problems. The first equation, of course, will be sum of forces in x. Let's get some coordinates on here so that has meaning. Sum of forces in y. But that's only two. So the third equation is the sum of moments. We'll have to pick some location on our rigid body here and sum the moments. And what is interesting is friction force can cause a moment. So for example, if we were to sum moments about, say, location 2 up here, Fn1 acts at a distance, so it has a moment arm, and F mu acts at a distance, and so it also has a moment arm. And so you'd have to keep that into consideration as we solve these problems. Keep in mind also that there are three types of friction problems. There are the problems with no apparent impending motion. These are the ones where we solve the force balance and discover that F mu is less than mu times Fn. In other words, we haven't hit that limit yet. Impending motion, the other two cases, either at all points of contact or some points of contact, those happen when F mu is exactly equal to mu times Fn. In other words, we're at the limit before this thing either breaks loose and starts sliding or starts accelerating. Keep in mind also that when you're doing these, really we're just adding one model equation to the mix, In other words, we're always going to solve problems using the same 4 steps. We're going to start by drawing a free body diagram, and that's going to include friction at the faces that it makes sense to include it. Next, we're going to perform our force balances and our moment balances. From there, we're going to discover that we have some geometry that needs done. This is where we resolve forces into their components. And lastly, we have some algebra usually to do to solve for the unknown that we're interested in. The last thing I like to say is when we're dealing with these 3 types of friction problems, you can think that if it's a no apparent impending motion problem, really what we're doing is we're just saying, okay, so what's the friction force that happens? A lot of times we'll just look for it directly. When we're dealing with impending motion problems, those usually look like questions asking, is this going to slide, or what's the maximum load before it slides, right? Anytime it's something like that where it's about to slide, we use F mu equals mu n, and we solve the equations or the force balances, and we just ask ourselves, is this equality true? In other words, when I set F mu equal to mu Fn, what's the biggest W that I could have? That'd be a great example for this problem. Either way, just follow the 4 steps and you'll see where it fits.